acids and bases, ionization constants of weak acids and bases. In this video, we will do a quick reminder of what weak acids and bases are, and then take this a bit further to learn what an acid and base ionization constant is and how to use it to tell the strength of an acid or base. We'll then do a calculation using pH to determine an acid's Ka. This will be an enormously useful quantity for us for the next few topics, and you'll want to have a good grasp before continuing on in the subject material. Be sure to notice, as we are going over this topic, that there really is no fundamental difference between this K, Ka and Kb, and the Kc and Kp that we talked about in earlier chapters. It's just another subscript to talk about another specific usage of the exact same mathematical idea. This should help to make this section less overwhelming. Let's quickly remember what a weak acid and base is. This is a molecule that, while it does donate or accept a hydrogen, it only does so in a very small quantity. In other words, it does not ionize completely, and that the equilibrium lies very far to the left. We can treat this nearly identical to how we treated the problems in the equilibrium chapter. There will even be a couple of ways that we'll see in later videos to simplify the calculations so that we don't have to constantly solve the quadratic equations like we did last chapter. Let's first talk about some definitions. Please be sure as we go along to think about how these definitions relate to what we talked about in previous chapters. We named the equilibrium constant for an acid the acid ionization constant. This will be written just like the equilibrium constants that we learned about in last chapter, the products over the reactants. Notice in this equation that water isn't included. Why do you think that is? Well, just like Kc and Kp, you don't include liquids or solids in the equilibrium constants. Kas are generally given in tables. You'll notice in most tables you won't see a Ka for strong acids. That doesn't mean that they don't exist. We just seldom talk about them because they are so large that we don't need to use it and can assume complete ionization. Let's think about the relation of acid strength to Ka. I have two examples drawn out. In one case, very little of the molecules are ionized, and then in the next, much more are ionized. This is of course exaggerated a bit for the sake of understanding the question, but you get the idea. Which of the two has a higher concentration of H+? Well, the one that is ionized more. That's the stronger acid. If you have a hard time remembering that, just think about what a strong acid is. It's something that dissociates nearly completely. So therefore, the more something dissociates, the stronger the acid is. Now, how does that affect Ka? You may want to pause and think about this for a bit. If you need a hint, look at the Ka equation. As the strength of the acid increases, what happens to each of the species in the equation? How does this affect the final number? Since stronger acids have more H+ and A- and less Ha, the Ka will increase. Therefore, the stronger the acid, the larger the Ka. Now that we have thought this process through, we can rank the strength of weak acids simply by knowing their Ka. The larger the Ka, the stronger the acid. For bases, it is very similar. Here, I will do both as a generic reaction, as well as an example, since weak bases are a bit tougher to see in the generic form. Just like other equilibrium constants we have learned, the base ionization constant is products over reactants, and liquids and solids are not included. For example, we can do ammonia. Both the ammonium ion and the hydroxide ion will be in the numerator, and the ammonia will be put in the denominator. It would be nice if we could judge the strength of a base by Kb, just as we talked about judging acids by Ka. So let's look at how the base's strength affects its Kb, so we'll have a rule to abide by when trying to determine how strong a weak base is. We'll approach this just like we did Ka and the acid strength a few slides back. If we have a stronger base, what does that mean about the equilibrium shift? Since a stronger base means that it shifts to the right to create more OH minus, then let's look at how that affects each species in the reaction. For the original base, we'll have less since more of it has ionized. We'll have more of the protonated base and the OH minus, since both of the products are increasing. Since both of the ones that are increasing are in the numerator and the one decreasing is in the denominator, the Kb must go up if the base is getting stronger, meaning that we can now rank how strong a base is by looking at the Kb. The stronger the base, the higher the Kb. Let's do one quick example of ranking acids in order of strength. Here I ask you to rank sulfuric, acetic, and formic acids in order of increasing strength. Let's first see if we can pick out the strongest without looking anything up. Hopefully you recognize that sulfuric is the only strong acid on the list and therefore must be the strongest of the three. For the other two, we need to look up some values. We skip to the back of the book or your favorite online table and look up both the Ka values. From here, the weakest will be the one with the lowest Ka, or acetic acid. So we can rank them in order of increasing strength, being acetic, then formic, then sulfuric acid. The exact same principle is true for bases, so we will skip doing an example. Note, there are ways to estimate the acid strength based on the properties of the bonded atoms as well, and we'll look at a few of these as chapters progress. For a more in-depth discussion, you'll have to wait till taking organic chemistry. Let's look at an example where we are given information and need to calculate the Ka. Given that you have a 2 molar weak acid solution and you measure the pH to be 3, find the Ka of the solution. For this, we need to know the quantities of each species at equilibrium. So we will go about this just like we did in the last chapter. For accounting purposes, it is typically easiest to use an ice table. Although it is far from required at this difficulty level, it's a good habit to get into. First, let's write out all the things that we need to know. We know that Ka is products over reactants. We also know that 10 to the negative pH is equal to the hydrogen ion concentration. Now let's write out the equation and start our ice chart. Because I don't know which weak acid it is, I've used a generic equation. We know that our initial value of Ha is 2 molar. The concentration of the acid always refers to how much you initially put in. We also know that we don't have any H3O plus or A minus, and so we can fill in zeros here. Now we need to think about what else we know. We know the pH, and that tells us what our equilibrium value of the H plus concentration is. Once we know that, we also know A minus because H3O plus and A minus must be the same since they all came from the HA. If we know that H3O plus and A minus are both 10 to the negative third, we also know how much of the initial acid dissociated since that is where the H plus and the A minus came from. Therefore, we also know our final concentration of the non-dissociated acid. Now that we know all three of our components, we can fill into the equation for Ka and get our final value. You should now understand what an acid and base ionization constant is. We're able to use those values to rank acids and bases in order of strength and calculate Ka using information such as initial acid concentration and pH.